Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and you'll get notifications for all the final review series and a bunch of other series on my channel. Basically what this one is this is video 5 in the Math 120 final review. So I'm going to do a whole bunch of more problems. Well, we're doing them 2 or 3 at a time. I think we'll do 2 in this one. We're going to do a number 11 and number 12. Again, I'm just arbitrarily counting through how many problems I've done so far. So in the first 4 videos we did 10 problems. I'm going to do a number 11 and number 12. What this one, number 11, wants is all the matrices involved are invertible, it tells us, and then it wants us to solve for the matrix X in this expression. Before we start that, let's list in my mind, and what should be clear for you, all the rules and the properties of inverses and matrices and the things that I'm going to want to manipulate this equation. Remember, this is a matrix equation, not a real number equation anymore, so we're going to use rules, but not all of the rules are exactly the same as for real numbers. First of all, we have 1. The inverse of a matrix is the matrix itself. 2. We do know that A times A inverse is the identity. That's the definition of the inverse. 3, but it's useful when we calculate. We're going to use this specifically. We know that I times any matrix leaves the matrix alone. We're going to use that somewhere along the line. We also want that 4, if we have A to the n minus, is also equal to A to the minus 1 to the n, which we're going to write as just A to the minus n. 5, what other one do we need? We need to know how to deal with 2. So if we're going to deal with A to the B inverse, and if A and B are both invertible, so is their product, and the inverse is B inverse A inverse. So you can distribute it, but it flips them. Remember, matrix multiplication is not commutative, so A times B does not equal B times A. So when I'm manipulating, I can't do that move. Also, I can't just flip stuff around. It has to be, when we multiply, it has to be both on the left or both on the right to cancel for matrices. The first thing that I'm going to deal with on both sides is I have the inverse of the inverse, and technically I'm going to write it as just applying this rule, the inverse on both sides. So this is if and only if X inverse A inverse inverse. So you can distribute it, but it flips their order, equals the same thing here. I can distribute this inverse, but it flips the order of them. If and only if B inverse inverse is equal to A inverse times AB squared. This was in brackets, notice. Now what I'm doing is using the property that an inverse of an inverse is A and the inverse of inverse is B. That gives me if and only if X inverse A is equal to B, and now I'm already going to associate, I am allowed to associate matrices, so this is A inverse A B squared. I know, hi, we got a visitor. He wants to see how to do matrix multiplication. This one's noodles. What do I do from there? Now I'm going to use that A inverse is the identity matrix. This is if and only if X inverse A is B times I times B squared. But what does B do to, or I do to B squared? Nothing. So this is equal to B times B cubed squared, which is by definition B cubed. I know you're a very nice boy. Okay. Now what do I want to do? I want to solve for X in this equation. What is that giving me? Okay, yeah, you go. That gives me, from here, I have now X minus X inverse A equals B cubed. So I'm trying to solve for X inverse. What I'm therefore going to do is inverse both sides so I can get at X. Let's do that. If and only if X inverse A inverse equals B cubed inverse. If and only if, again I'm flipping this, this gives me A inverse X inverse inverse equals B to the negative 3. We're using the power rule now. This one technically, I don't have to write that step, but I'm going one at a time. This is now if and only if A inverse x equals b to the minus 3. And now I left space specifically because what I'm going to do now is multiply both sides on the left by a to get rid of the a inverse. So I'm multiplying both sides by a. What does that give me? That gives me here now, you can see I would associate, so I associate the brackets, that gives me a inverse x equals a b minus 3. This becomes identity. So this is if and only if identity times x is equal to a b minus 3. And so that's if and only if identity doesn't do anything. This leaves me with x is a b minus 3. So go through that slower if you want in each step, but analyze in each step, each if and only if. I'm trying to do one move at a time, and I'm just using the rules that I listed ahead of time systematically to solve for x. Next question, 12. Okay, what 12 wants is, 12 wants me to find the general equation of the plane P passing through the points P, Q, and R. This is essentially all I need to describe the plane. First of all, before I start, I draw myself a picture. There's P, so I can picture in my mind, and then it says I have P and Q and R, so I'm going to write this as arbitrarily labeling them. Suppose this is P, and this is Q, and this is R. Then what I'm going to do is I need to describe any kind of avatar for a plane, whether it's the parametric or the normal form or the general equation, whichever one I'm trying to build. I need a point on the plane and then two vectors in the plane to either use those for the parametric or create the normal vector, which will be the cross product of the two vectors laying in the plane. I'm flush with points. I've got P, Q, and R, so I have that if I need. And what I need is two vectors in my plane. How I create those are U will be PQ and V will be PR. This says U is equal to PQ, which is equal to Q minus P as vectors, which is equal to Q is 2, 1, 1, minus, 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 1, 1, minus 1. So this equals the vector 1, 0, 2. And V is going to equal PR, which is R minus P as vectors, which is the vectors R, 1, minus 1, 2, minus, 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 1, 1, minus 1, which is equal to the vector 0, negative 2, 3. Now I have two vectors, U and V, laying in my plane. What I do with that now is I need to create the normal vector from that. The normal vector N, which we call ABC in general. That's found by computing the cross product of U and V. And notice that N will be orthogonal to both U and V. Let's do that using U and V. U cross V is equal to I, J, K, U, 1, 0, 2, B, 0, negative 2, 3. Cofactor expansion along the top row is I times the 2 by 2 determinant blocking off row 1 and column 1, which is 0, 2, negative 2, 3, minus J times the 2 by 2 minor obtained by blocking off row 1 and column 2, so I get 1, 2, 0, and 3, and plus K times the 2 by 2 subdeterminant obtained by blocking off row 1 and column 3, so 1, 0, 0, negative 2. This gives me the vector I times 0 minus minus 4 is 4, minus J times the vector 3 minus 0, which is 3, and plus K, the vector K times negative 2 minus 0, so negative 2. This gives me the vector, remember I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. So this gives me the vector after adding and scalar multiplying 4, negative 3, negative 2. you have a check. Since we just got u cross v, and I just pointed out before I started, they have to be orthogonal to both. What's the Pavlovian reflex there? Their dot product is 0. That's right, their dot product is 0. Check it quickly. What's the dot product of this vector and u? This will be times dot product with 1, 0, 2, which is equal to 4 plus 0 minus 4. Yes, the dot product is 0. If you check with v, it will be the same thing, so this is the correct vector. It's orthogonal to both. What do I do with that? Now that I have n, this is our normal vector, n. From this, we now need n dot product r minus r naught equals 0 is the normal equation. We simplify that to get the general equation. What do we have? We have n. What do we need? R minus r naught. Remember, this is x, y, z minus one of our points. I'm going to use this point. R minus r naught is equal to x, y, z minus 1, 1 minus 1, which is plus 1. Now this equation is this guy dot product with this one. This gives me 4, -3, -2 dot product with x minus 1, y minus 1, z plus 1 equals 0. If and only if, by definition of dot product, this times this plus this times this plus this times this. So 4x minus 1 minus 3, y minus 1 minus 2 times z plus 1 equals 0 is the normal equation. And then simplifying gives me the general equation. This gives me 4x minus 3y minus 2z minus 4 plus 3 is -1 minus 2 is -3 minus 3 equals 0. This is the general equation of that plane through points P, Q, and R. Please subscribe right here. You'll get notifications, as I said, to this series and many others on my channel. I'll see you next time.